This case study demonstrates principles for achieving a socially sustainable community in a very tall building, while providing levels for living amenity usually associated with street-level horizontal housing. Urban environments can be hostile to natural systems, and yet people need natural systems in order to live. This case study integrates nature into a vertical form where the case study seeks to demonstrate that this is feasible, whilst achieving a high standard in the quality of life and social amenity for people. Architecture can be viewed as an extension of the landscape in ways that buildings contribute to the restoration of ecosystem health. One objective for the case study was to design a very tall building that could sustain a 500-year life. A second objective was that the building should provide multiple opportunities for connectedness compatible with socially sustainable communities. The design process was driven by sustainable principles throughout. The case study adopted a long-term focus and a wide-casting approach to urban design. Adaptability for future changes and allowances for technological developments was a key driver to the planning throughout the case study design. Therefore, in support of the building's long lifespan requirement, planning elements and systems are designed to be as simple and robust as possible. The building is 120 stories high with a height of 545 metres and a full height free-form atrium intersected with 6 community gardens. The atrium has a short axis of 90 metres and a long axis of approximately 140 metres. The design principles developed in this study confirm, however, that the principles are just as valid for towers of lesser heights, whether 20, 40 or 60 metres. Or 60 stories, I should say. 20, 40 or 60 stories. All apartments have a degree of indoor-outdoor living and deep soil gardens that provide recreational support, as well as the advantages of microclimatic improvements. This amount of outdoor area represents a level of amenity that is more equivalent to that of horizontal street-level housing than conventional vertical residential developments. Simplicity of elements, a long life cycle, services accessibility and other design drivers generated the separation of building components into discrete elements reflecting their different life cycles and functions. Most directly, the apartments of all sizes form separate construction shells within the structural frames. This is a crucial difference. Apartment design can change throughout the life of the building. The primary megastructure carries all of the structural loads. Flexibility is possible for the selection of materials for the secondary and tertiary systems. Significant opportunities are possible for prefabrication and flat pack installation processes. The spatial planning reflects a building form that provides for loose fit processes for future development without the form of the building changing. The separation of building elements includes the lift shafts, fire stairs and services risers located in the atrium. 3 independent sub-towers of 120 metres and 80 metres in height, in length, 120 metres in length and 80 metres in length, surround the open core. The plan form reflects the requirements for optimising solar access, breeze flow, multiple outlooks, advantages for the staging of construction, structural stability, site flexibility, climatic responsiveness, and sustainable design parameters. The planning elements are illustrated in the spatial model of the next slide. The design eliminated, as I said, the need for a central lift and services core. The structural design renders such a core redundant. Multiple lifts are designed in a distributed pattern appropriate for proximity to residences and the location of express or local stopping lifts. Similarly, fire stairs are distributed throughout the atrium, focusing on short paths of travel, direct line of sight visibility, and ease of navigation in an emergency. Modules in apartments are confined to a single depth to provide effective cross-ventilation and social connections as each apartment opens onto communal space rather than a corridor. This is important for creating conditions that support natural social interaction, as in walking along a street in front of your home. Operable glazed windscreens in the atrium perimeter control cross-flow ventilation, pressure equalisation and stack venting suitable for the siting, geography and climate for each specific project location. Two typical residential modules were chosen, namely a single bedroom apartment and a townhouse type 2-level apartment. However, a broad range of apartment types are possible with this design approach. The structural module forms a volume 12 metres wide, clear span, by 16 metres high and 18 metres deep. This creates a plan area of 216 square metres per module. Each module can accommodate 2 townhouses, each of 2 levels, and each within a volume of 8 metres per townhouse, 8 metres high, or 8 single-bedroom apartments of 48 square metres in size. Single paths are required for only every 2 levels. So access paths are required only for every 2 levels, except for the wing with the 1-bedroom apartments, in which case a walkway occurs at each level. The structural module is contained on all sides by a 1.2 metre deep structural and services zone, which also incorporates water storage systems of fire services, garden irrigation and grey water treatment for recycling. The outside and inner faces are unobstructed structurally due to the structural free span of 12 metres per module mentioned before. Windshield and solar screens form the external facades of each module. The perforated diaphragm shear wall also acts as an important spatial transition between the public and private realms for the residents, and Andrew will talk at length on this a little bit later. The 3 sub-towers vary in height, with the shortest height at 72 metres, 88 for the middle wing, and 120 levels for the tallest. This form reflects the structural performance characteristics of a very tall building and will be discussed, as I said, a little bit later. Traditional town planning and building regulatory processes are as applicable and valid for this case study as they currently operate for conventional building types. The case study opens up opportunities for financial models to be involved that are currently mostly applicable only for ground level development. The 1-bedroom apartments explore the opportunity for indoor-outdoor living and shared multi-level height for accommodating 6-metre plus tree species, a scale of tree which is normally associated with small ground-level courtyards. This level of amenity provides a high quality of living and general well-being. Balconies across the front continue around the sides of the apartments to provide a sense of spaciousness and options for relaxation. Canopies of trees below contribute to a feeling of nature for the units above. So there's an overlapping of the benefit. The next 3 slides demonstrate the climatic adaptability of the case study. With the temperate climate model, operable windshields and solar screens ensure a comfortable level of amenity in a wide range of climatic and weather conditions. Indoor-outdoor living is practical. The deep soil gardens generate the many advantages of an effective microclimate. Not only do the operable facades provide the building with an environmental responsiveness to different climates, but also, most importantly, to cultural contexts, as shown here in a hot, arid climate. In another example, outdoor living can be enjoyed in tropical climates with the benefit of breeze flow while having protection from monsoonal rain. The townhouse design is just one example of what is possible in the sky allotment for family living. Adaptability of the modules provides for changing household dynamics and contributes to family long-term well-being and stability. The flexibility of the apartment construction allows for multiple generations of families to live in the same module, assisting social support of a family unit, as well as intergenerational cohesion. The structural module is similar to a parcel of land that is 216 square metres in area. Flexibility in style, configuration and materials gives each module individuality not readily available in conventional high-rise apartment buildings. This sustainable vertical urbanism model is more closely aligned to ground-level terrace house living. The next 3 slides show different models carried out for 3 different climates. Suitable for all contexts, the quality of the space creates a sense of living in a house rather than an apartment. The integrated deep soil garden zones regulate the apartment microclimate with humidity control, ambient temperature and air quality, including filtering dust and increasing the amount of fresh oxygen. The 8-metre module height provides high levels of daylight and solar access. The landscaping for hot, arid climates provides humidity, filtering of airborne dust, and additional degrees of shade that shield the building surfaces from solar gain. Microclimatic cooling reduces the necessity for air conditioning and internal spaces. Transitional indoor-outdoor living becomes possible even in the middle of the day, which is not usually possible in hot, arid climates, such as we see in the Middle East. In a tropical climate, the garden microclimate and building design regulates the tropical extremes of monsoonal rain, high winds and high humidity. Urban design principles used in conventional ground plane town planning provide a range of regional parks, urban forest buffer zones and local neighbourhood parks. In this case study, these same urban design scales and principles have been transferred into the vertical dimension. That is, a 3-dimensional relationship that retains all of the possibilities for social interactions. The gardens are a key component of socially connecting people, and that is one of the most important principles of the whole concept. The design provides for a range of gardens from the broad-scale ground-level urban forest, neighbourhood sky gardens, pocket parks, and finally the private gardens that are a feature of all apartments. Water is proposed to be recycled and filtered through all of the gardens, whether common areas or the private apartments. The case study building would likely generate 3 times the active carbon storage as a greenfield site. The restorative well-being of residents and the power of rejuvenation is possible by providing access to nature. Conventionally designed high-rise buildings lack a most effective factor for the well-being of humans, namely the well-researched biophilic relationship between ecosystems and humans. The building incorporates 6 vertical neighbourhoods or villages, each centred around an open atrium sky garden, separated 20 levels apart. 6 atrium gardens provide multiple opportunities for social interactions, facilities such as a local shop or cafe, and the gardens provide opportunities for recreation, such as Tai Chi or adventure playgrounds for children. The view of a project from nearby buildings and neighbouring units is an important consideration. How a building contributes to the outlook of its neighbours is vitally important in creating quality urban environment. Each building becomes the topographical feature of its neighbours, which is all the more challenging for very tall buildings. The near view influences the sense of urban texture and quality of neighbourhood. It also contributes to a community awareness of others and needs to consider privacy in the urban context. Hence the importance of transitional exterior spaces in very tall buildings. Continuity of landscaping is important at ground level. This is a view of the atrium garden entry lobby at ground level. The ground level garden planting continues through the 32-metre high void under the building. This height allows for sunlight to penetrate, as well as making connections with planting that could form biodiversity corridors within an urban environment. The building lobby is a 32-metre high urban forest, and the first habitable levels begin 32 metres above ground level. Unlike the more conventional approach to site development, the land surface has not been alienated and removed from the all-important air-soil-plant-root interaction. The top layer of the soil, namely the rhizosphere, contains the intense concentration of biological and chemical activity associated with plant root and soil interface, and this remains intact, as shown in this case study. I'll now hand over to Andrew to discuss the structural aspects of the project.
Thanks, Richard. Richard touched on the functional relationship between the functional planning and space planning of the building and the structure, particularly to do with the block elements here, or the three wings. But probably the most complicated component for us of dealing with this building was how do we put in an intrinsic stability system that enables this building to inhabit sites where you may go from 100 metres to 500 plus, maybe 1,000, but also in various parts of the world where the climatic conditions are different. So in plan form here, perhaps these blocks are adjusted in geometry, and perhaps also the perforation changes due to solar access, wind, and also then structurally our loading regimes in high seismic zones, in high wind areas, but also geographies where materiality changes and varies. So how do we come up with a system that can be translated across all of those different elements and is intrinsic to the building? The block structures themselves are reasonably conventional in their grid and their spacing. So for us it was about how do we tie those together and we do it flexibly. So I suppose the backbone of the system here is the provision of a tube around the inside, and this tube is really an organic system that's perforated at will, provides all of the primary stability, and it's flexible. So you see here, if these blocks change, we can change the building and provide different torsional shear stiffness or flexural stiffness depending on how we want to configure the building, its height and its loading regime. It runs along the edge of the blocks here. As Richard said, it's perforated every 2 floors for access to the building, but also, obviously, we'd like to minimise materiality and perforate and only put as much material in as we see fit. So that would relate to the structural loading at the various heights and based on the form. The large holes through here are coupled by these connections, which we'd propose to do helically around the building, performing a bracing function as well as just out of a frame. And the organic form then becomes stiffened by the block walls that sit here inside the individual blocks. At the garden levels, then, in plan, the main garden levels provide diaphragms around 86 metres between those diaphragms, and then the individual blocks span between those diaphragms. And then we then get a holistic system of approximately 90 metres across, which gives us great width to deal with. The blade walls or frames that also stiffen this curved wall also give us perimeter area in flexural and overturning. Secondary structure is provided in the service risers and the cores to support the main diaphragms and the egress slabs, so they don't form a part of the primary stability system. And then finally, within the crate of the zones in here, as Richard pointed earlier, are the tertiary systems. So those pieces of structure that we want to see change as people live perhaps in the building through different generations and their requirements are different. So we see this primary structure being able to be developed in either conventional materials such as concrete or steel suitably for the location. But the tertiary systems in here really do lend themselves to materials like timber, CLT, where they are dry systems that can be changed and adapted over the life of the building, but also capture carbon and contribute to the sustainable nature of the building.
Sydney, Australia was used to provide an example of urban modelling. The Sydney metropolitan region covers 1,730 square kilometres, with a population of 4.5 million people. Image 1 presents the inner region of that metropolitan area today, centred around Sydney Harbour. Using this case study as a metric, Image 2 shows 900 residential towers located within the inner region of Sydney. These 900 towers, as shown in the case study, each houses 5,000 people approximately. So 900 towers could accommodate 4.5 million residents. That is the entire population of Sydney. Image 3 graphically conveys how extensively green space can be generated using this residential typology for sustainable vertical urban development. This demonstrates the green space potential that can be achieved instead of urban sprawl as our cities expand. Ecosystem restoration and health can be returned to the land, and urban agriculture would once again become a reality, as it was during the earlier years of development of our modern cities. This example graphically illustrates the potential for green urban renewal and the cessation of urban sprawl. It is possible for new forms of sustainable vertical urbanism, such as proposed in this case study, to provide high levels of amenity and social sustainability. The case study design supports the urban density required to optimise efficient, economical public transport. It also frees land for greenbelt corridors that would contribute ecosystem services for clean air, water and enhanced human health. The case study design provides an example that illustrates how urban development and population growth can be supported while providing high levels of amenity, socially sustainable living and restored ecosystems. Ecosystem restoration and urban development can be compatible. The challenge is that new building typologies are required to achieve vertical sustainable urbanism.